Hello. What are we doing here? Yeah. So is it still working? Yeah, I guess so. Last class we took a Java program and compiled it into a Turing machine using first order logic. And now we're going to talk about a universal Turing machine, which is an important thing. All right, so and again, what we're just doing here is working on being able to say things in first order logic. And since we need to do examples anyway, we might as well do examples that you're going to need in the future. All right. So we can we can write. The next topic is to be able to. Well, I mean, here's the statement that we can be able to say in first order logic, which we're going to do next, which is saying you have a fixed Turing machine M, and you give me an input represented as an integer, and you give me a y, an output represented as an integer, and we say that the statement will be true if the Turing machine on the input gives me this output, right? So we can say that in logic. And this is certainly, Turing was all about defining the Turing machine, right? It's a simple, what is a Turing machine? It's just a simple model. And what it has at every point in time, it's in some state, and it has some infinite tape, which is filled up finitely with zeros and ones, and it has a head. And then what happens is, if you're in a given state and the head is looking at a given character, then it changes state, it writes some character on the tape, and it changes direction and it moves the head, right? That's all it does, right? All right, so there's the current state, there's the character seen, there's the next state, there's what to write on the tape, there's the direction to move the head. And all right, so that's what a Turing machine is. And what does my laptop do? Right, we have one sitting over there. Well, one thing you can do with a laptop is you can give it Java code as a file, and it's stored in binary, which can be concatenated together to be a big integer. And you can give it some input, and it will run the Java program on the input, right? And return the result. So the Java program can do this, right? You give it a Java program and an input, and it tells you what the Java program does, right? Everybody agree with that? So similarly, you could give the laptop a description of the Turing machine, and it could then compile the Turing machine. It could simulate the Turing machine, right? It could do that just as well. And then we can believe it can do that. And we also talked about, well, how is the laptop running? Well, maybe it wasn't written in Java, but it was written in some programming language. And we were told that last class, we talked about how you can compile a program into a Turing machine, right? So you can, all right, oh yeah, those were just the statements we said before, right? The laptop can, given one of these things, output one of those things, right? No, it is a Turing machine. All right, so here's a Turing machine that pretends to be the laptop. And what it does is you give it a Turing machine, and it says what that Turing machine does, right? So we call this a universal Turing machine, right? It's one Turing machine. There's a description of one Turing machine that you can give it any Turing machine and it'll run it, right? And so yeah, so that's just, it's one Turing machine and it simulates it. And so here's the statement, right? We're doing first order logic. What are we saying? If you play the game, we're saying there exists one Turing machine, right? How do you define a Turing machine? You tell me what the states are and what the state transitions are. And then you come over here and the adversary gives you as input to your Turing machine the description of another Turing machine, right? Now, what's surprising is you might say, well, what's true about a Turing machine? It has some number of states. It has some tape alphabet, which could be 0, 1, or it could be bigger, right? And you've already fixed the description of this Turing machine, right? Because it exists. And then the adversary gives me a bigger Turing machine, right? There exists one Turing machine where any Turing machine you give me, so you give me a bigger Turing machine with more states and bigger tape alphabet, right? And the small Turing machine can simulate it, right? Does that make sense? So it is kind of an impressive thing, which if you take 2001 from me next term, you will learn how to do. And it's very useful. I mean, that's what computers are doing all the time. One machine is running another machine, right? And in fact, we're going to talk about Gödel, a logic guy, and he came up with a model of computation. And the one thing his model wasn't able to do is to have a fixed version program in his model run another program in his model. He couldn't do that, and that's why it wasn't a universal Turing machine.